All right, welcome to the deep dive. We're diving into something well, it's really captured the attention of everyone here. I think you'll find this one pretty fascinating.
Yeah, this is a paper that, well, it kind of throws a wrench into some of the, some of the accepted wisdom in AI these days.
That's a good way to put it. The paper is called Transformers Without Normalization. And yeah, that title alone, it's like, okay, this is going to be interesting. We've been kind of taking it as gospel that you need these normalization layers, especially with transformers.
Right, and we've got excerpts from the paper itself. It just came out, just dropped on the 14th of March, 2025.
So hot off the presses.
Definitely hot off the presses. And we've been digging into it, pulling out some of the key highlights.
Yeah, and I've got some of my own notes here just to try to, put it all in context. How does this fit into the broader world of deep learning and where we've been with these kinds of techniques?
And for anyone listening, our goal here is to really try to, give you that shortcut to understanding what this dynamic 10, this DIDT, what that actually is, why it might be a big deal. And then what are the implications, for the future of how we think about designing these models.
Right, because this could be one of those things that ripples out and changes the way we do things going forward.
Absolutely.
So let's back up a little bit. I mean, for folks who maybe haven't been, super deep in the AI world, normalization layers, they've kind of become like a standard ingredient in the recipe. We've seen batch norm come on the scene back in 2015, and that kind of kicked things off. Then you had layer norm, RNS norm, and the idea is as these networks get really big, really deep, really complex, the signals inside, the numbers bouncing around, they can start to get out of whack.
Yeah, they can explode, they can vanish. It becomes very difficult to actually train these models effectively.
Right. So normalization, it's kind of like I don't know, it's like putting in those rumble strips on the side of the road to keep you from, going off the edge. It kind of keeps everything within a reasonable range.
That's a great analogy, actually.
And as these models have just exploded in size, we're talking billions, even trillions of parameters, these normalization techniques. It's been like, okay, like you got to have these in there to make it work.
It's been almost taken for granted that, if you're going to train something really large, you need some form of normalization to keep it stable. And importantly, transformers, right? Which have become, they're the foundation for so much in AI now, from language models to vision to, just about everything. They rely heavily on layer norm. Even all these new architectures that people are coming up with, you almost always seen some form of normalization tucked in there. So this paper comes along and says, wait a minute, what if we don't actually need that in transformers? It's a pretty bold statement.
Yeah. Yeah, it's like questioning one of the fundamental building blocks. And I think that's what makes this so interesting is that they started with this question, is normalization truly indispensable? And that's not a question I think a lot of people were even asking. It's just become so ingrained in how we do things.
Yeah, yeah, and what's remarkable is the observation that led them to their innovation. Sometimes the simplest things are the most impactful. They notice that layer normalization in practice, it often does something very specific to the data. If you were to kind of visualize, you take the input to a layer norm layer and you look at the output and you plot those, against each other, you often see this curve that looks remarkably like a 10 function, that classic, S shape, that kind of smooth curve. So essentially what layer norm is doing is it's taking the input values, it's scaling them, and then it's kind of squashing the extremes, right? It's keeping things from getting too high or too low.
Okay, so they're saying that this complex operation that we've been using, this layer norm, it might actually be mimicking a much simpler mathematical function.
Exactly. Exactly. And they actually visualize this, in the paper. They show it graphically. If you look at figure 2, they've got these plots for, different transformer-based models. Vision transformer, VIT, Wave 2 Vec 2.0 for speech, DIT, which is used for generating images. And you can see how even though layer norm technically, it's applying a linear transformation to each individual token, the overall effect is nonlinear. It's like a scaled tandem function.
That's pretty amazing. So then they took that observation and they said, okay, well, what if we just cut out the middleman here?
Yeah, exactly. So they introduced this new operation called Dynamic Tan, or DIT for short. Now the basic form of it is actually pretty straightforward. It's tan of alpha x plus beta but they refined it with a couple of additional parameters to dietiacinegs equals gamma, tan, alpha X plus beta. Now, don't let the mathematical notations scale you off. The key is what those parameters actually do. The tan of alpha X part, that's the core of it, and it's an element-wise operation. So what that means is it's applied to each individual value in the data, right? So if you have a vector of numbers, each of those numbers gets passed through this tan function. Now the alpha, this is where it gets interesting. Alpha is a learnable scalar parameter. So what learnable means is that as the model is training, as it's figuring out how to do its task, it's also figuring out what the best value for alpha is. And ALU controls how much the input gets scaled before it goes into the tan function. So it's basically it's dynamically adjusting that scaling factor. And then you've got beta and gamma. These are also learnable, but they are per channel. So think of if you have an image with different color channels red, green, blue, you can adjust these parameters independently for each channel. So maybe you want to shift the red channel a little bit differently than you want to shift the blue channel.
So in a way, it's kind of like you got those knobs on a sound mixer, right? And you can adjust each channel individually.
Exactly. It gives the model a lot more flexibility in how it's transforming the data.
Okay, so DIT, it's essentially doing something similar to normalization, right? It's scaling, it's squashing, but it's doing it directly through this modified tan function without needing to calculate all those statistics like the mean and the variance.
Yeah, it's much more direct and potentially more efficient, which we'll get into. But what's really remarkable is that they didn't just stop at proposing this idea. They put it through its paces. They tested it on a huge range of AI tasks, different model architectures, different data sets. They really wanted to see, does this actually work? And spoiler alert, it does. It works surprisingly well.
Yeah, they didn't just stick it on one toy problem and say, "Oh, look, it works." They really threw the kitchen sink at it. So, let's talk through some of those findings. So first up, computer vision. This is one of the core areas of AI. They looked at image classification, object detection, all the usual suspects, and they tested it on ImageNet, which is this massive data set of labeled images. They used different architectures, vision transformers, Conv and across the board, they found that DIT performed at least as well, sometimes even a bit better than layer norm.
And what's interesting, if you look at figure 5 in the paper, they show these learning curves, how the models are learning over time. And the curves for the models using DIT and the ones using layer norm, they're remarkably similar. So it suggests that they're learning in a very comparable way.
Right. So it's not like DIT is learning in some completely bizarre off the wall fashion. It's following a similar trajectory.
It's finding a similar path to a good solution.
Now, they also looked at self-supervised learning, right? Which is this really powerful technique where you don't need labeled data. The model can kind of learn by itself just by looking at tons of examples. And they used popular methods like MAE, masked autoencoders, and Dino. And again, they're finding that in these pre-training tasks, DIT is right up there with layer norm.
And it's consistent, right? Across different architectures, across different tasks, DIT is holding its own against layer norm.
Okay, now let's talk about image generation. This is where things get really, really exciting. They used diffusion transformer models, DIT, and they tested on ImageNet. And here's the thing, in some cases, DIT actually achieved better scores on those key metrics like FID, fresh A inception distance, which measures how realistic and how diverse the generated images are. So not only is it keeping up, it's actually pulling ahead in some cases.
That's really intriguing, and it suggests that there might be something about this dynamic Tanh approach that's actually beneficial for these generative tasks.
Yeah, it's not just a neutral replacement. It might actually be unlocking some new capabilities. Now, the big one, right, the one that everyone's really excited about is language models. And they tested this on Llama, the large language model Meta AI released. And they scaled it all the way up to the 70 billion parameter version. Now, Llama traditionally uses RMS norm, and they swapped that out for DIT.
And what they found was that the training loss was very similar. The zero shot performance, which is how well the model can perform on tasks it hasn't specifically been trained on, was comparable. So again, it's holding its own against the established normalization techniques. Now, one caveat here is that they did find it necessary to add this extra learnable scalar right after the initial embedding layer in a llama when they're using Daiti, just to ensure stable training. But other than that, pretty much a drop-in replacement.
That's pretty amazing. And they didn't stop there. They also looked at speech processing with Wave 2 Vec 2.0, which is used for things like speech recognition, speech synthesis, and they even looked at DNA sequence modeling, which is, a whole other area of AI, using models like high-ended DNA and Caduceus. So it's really remarkable how broadly applicable this seems to be.
It really speaks to the generality of the approach. It's not just tailored to one specific type of data or one specific type of model.
Yeah, and let's not forget about efficiency. I mean, these models are getting so huge, the computational cost is a real concern. And they found that with DIT, you can actually get significant speed ups in both inference, which is, running the model to make predictions, and in training, which is, actually teaching the model.
Yeah, and this is where those computational savings really start to matter, right? Because if you can train a model faster, if you can run it faster, that opens up a whole range of new possibilities in terms of what you can do with it.
And they did some really interesting experiments to kind of dissect, why is this working? So they did these things called ablation studies, where they basically took DIT apart and they said, okay, what if we remove this piece? What if we tweak this parameter? And they found that, that tan function, that S-shaped curve, that's really, really important. If you replace it with something else, another nonlinear function, performance drops.
Yeah, so it's not just that, any nonlinearity will do. There's something special about that tan function, that S-shaped curve that seems to be really crucial for making this whole thing work. And they found that, that learnable alpha parameter, the one that controls the scaling, that's also really important. If you take that away, performance takes a hit.
Right. It's like each piece of this puzzle is really contributing to the overall success.
It's a very elegant solution, It's simple, but it's effective.
Now they also looked at how alpha, how that parameter changes during training. And what they found is that it's actually kind of it's adapting. It's tracking the inverse standard deviation of the activations, which is, a measure of how much the internal signals are varying. So it's almost like it's dynamically adjusting itself to keep those signals within the right range for the tan function to work its magic.
It's almost like the network is learning its own form of normalization. It's figuring out how to scale things appropriately without having to explicitly calculate those statistics.
That's pretty cool. Now, they also compared DIT to some other methods that have been proposed for training transformers without normalization.
Yeah, there have been a few, other attempts to do this, but what they found was that, across a range of tasks, Daiti consistently outperformed these other methods, even after they did this, careful tuning of the learning rate, because some of these other methods are really sensitive to how quickly the model is learning.
Right. So it's not just that, it works under ideal conditions. It's actually more robust. It's more reliable.
Yeah, and then they delved into this question of initialization. When you start training a model, you have to give those parameters some initial values. And they found that for most models, if you're not dealing with these absolutely massive language models, the initial value of alpha, it's not that critical. You can set it to a reasonable value and things will generally work out.
Okay. So you don't have to be, super precise about it.
Right, but when you get to these really, really large language models, the ones with billions and billions of parameters, then the initial value of alpha does start to matter. And what they found was that the larger the model, the smaller the initial value of alpha needs to be.
So it's almost like, you have to be a little more careful. You have to kind of ease it in, with these really, really large models.
Exactly. And what was really interesting is that they found that different layers within the model actually benefit from different initial values of alpha. So, the attention layers, they like a higher initial value. The feed forward networks, they like a lower initial value. So it's not just a one size fits all kind of thing.
You gotta tune it. You gotta tailor it to the specific architecture.
Right. And they also found that the width of the model, how many neurons are in each layer, that seemed to be a more important factor than the depth of the model, how many layers there are. in determining what the optimal initial value of alpha should be.
That's a really interesting observation. So all in all, this dynamic ton, it seems like a really promising alternative to traditional normalization. But as with any new research, there are always limitations, right? There are always things that we still need to explore and understand.
Absolutely. And the researchers were very upfront about this. They acknowledged that, deity might not be a universal replacement for all types of normalization. Specifically, they found that it didn't work as well when they tried to replace batch norm in convolutional neural networks, the ResNets and the VGGs of the world.
So there's still some work to be done there. Maybe there's a way to adapt it. Maybe there's something else going on that we need to figure out.
Yeah, their hypothesis was that, batch norm is used very differently in convolutional networks than layer norm is used in transformers. So it's not a simple one-to-one mapping.
Okay, so let's step back and kind of bring it all together. The big takeaway here is that this research, it's really challenging this assumption that we've had for so long that normalization layers are absolutely essential for training these powerful models, especially transformers.
And what's remarkable is that the solution they came up with, this dynamic tan, it's so elegant. It's so simple, yet it seems to be, just as effective, if not more so, than the more complex normalization techniques that we've been using. And it has the potential to make these models faster, more efficient, which is a huge win.
And the key insight here, the one that I think is just so cool, is that, layer norm, it's basically mimicking this simple tan function. And once they realized that, it opened up this whole new way of thinking about how to achieve the same outcome, but in a much more streamlined, much more efficient way.
It's a beautiful example of how, really deep understanding of what's going on under the hood can lead to these really elegant and powerful solutions.
So what does this mean for you, for the listener? Well, this could lead to faster, more efficient AI models that are cheaper to train, cheaper to run. That means, we can do more with less. And it could also open up new possibilities for deploying AI, on devices with limited resources. Think about smartphones, think about, edge devices, all these things that don't have the horsepower of a big data center.
Absolutely. And it also, it deepens our understanding of how these models work. And that in itself is incredibly valuable because it allows us to design better models, to understand the limitations of current models, and to push the boundaries of what's possible.
It's like we're peeling back the layers of the onion, right? We're getting a little closer to understanding the fundamental principles at work here. And that's always a good thing.
Yeah. And it also, it makes you wonder if something as fundamental as normalization can be, potentially replaced or simplified in this way. What other assumption that we're making, in AI, in deep learning? What other things are we taking for granted that maybe we shouldn't be?
That's a really good question. And it's the kind of question that should be driving more research, right? What are those secret cows that we need to poke at, to see if maybe there's a better way.
And that's what's so exciting about research in this field, right? It's constantly evolving. We're constantly learning new things, and sometimes those new things completely change our perspective on how things work.
Yeah, it's a humbling reminder that we don't have all the answers yet. And that's okay. It's what makes this whole journey so interesting. So if you're intrigued by this, if you want to dig in a little deeper, definitely check out the paper itself. It's on ArcSieve. The identifier is ArcSieve 2503.10622V1. They also have a project page where you can find more information. You can find the code if you want to, play around with it yourself. It's jiachenju.github.io/dyt. And yeah, I think we've only just scratched the surface here. This is something that I think we're going to be talking about for quite a while.
Yeah, it's definitely one to watch. I have a feeling this is going to have some pretty significant ripple effects in the field.
Yeah, I think so too. So keep an eye out for more developments on this front. And until next time, happy diving.
Happy diving.